Okie doke. Well, welcome to these lectures on the Standard Model. You've had already a week's worth of lectures on different topics. And these ones on the Standard Model are going to hopefully give you a sense of the sort of, what I'm hoping for is that they will give you a sense of the sort of the structural aspects of the Standard Model. And the idea behind this is so that you can understand the Standard Model in particle physics, and how one goes about calculating, for example, or at least estimating event rates at particle detectors, but also to give you a sense of the sort of structural questions that we're interested in that take us beyond the Standard Model. Why when theorists propose theories beyond the Standard Model, the sort of questions they're hoping to address, so that when you confront these topics in the future, you will be well equipped to really understand where they're coming from without having to sort of go and do some research into these problems. So what is the Standard Model? That's essentially the goal. We're going to answer that question in these lectures. If I were to sum it up in one sentence, I would say it's basically the greatest intellectual achievement of humankind. For many reasons, and I hope you will come to appreciate that over the course of these lectures. There are some topics that I want to cover. I've put 9 topics on these 2 boards. However, there are 9 lectures, and my initial goal was that during these 9 lectures, we would be able to cover each of these topics in one sort of isolated unit. However, I'm also very realistic that the timing may not work out exactly the way I've planned. So instead, this is a list of 9 topics that I want to cover. And I hope we will get through all of them, but we may not. And I may have to rush a little bit in the last lecture and compact some of these topics into one lecture or something like that. So these topics are, what is the Standard Model? And that's number 1. And in this first lecture, which will be today, I really wanted to discuss sort of where it comes from, what is the structure, how it's framed within the context of theories themselves, to give you a sense of the grounding, the sort of foundations. Now, this is not going to be in any sense inspired by chronology. So one often an approach of teaching the basics of the Standard Model is to sort of go in tandem with the historical development of the Standard Model and understanding, for example, how the theory of QCD, for instance, was developed in the 70s and so on. I'm not going to do that. I'm going to give you really what I perceive to be a theorist's view of the Standard Model. So it's very much structural, and it's very much in terms of framed in terms of a sort of a recipe of how to build quantum field theories. And if you want to understand more about the history and the development, you should go and look that up yourself. It's an absolutely fascinating topic, and it's almost more intriguing to go and revisit the history of the development of the Standard Model once you understand it structurally, because you can sort of see the path that our incredible forebears were on as they were piecing this thing together. So I'm going to give a sense of the structure today. In the second lecture, I want to discuss the symmetries of the Standard Model. Basically, theories, mathematical theories, physical theories are underpinned by symmetries. And always, in my opinion, the right language for describing physical phenomena is symmetries, whether these are exact symmetries, gauge symmetries, approximate symmetries, accidental symmetries. Always one can, I believe one can get most rapidly to a quick estimate, sort of like Fermi would do on the back of an envelope, most rapidly by using symmetries. And so I want to have an entire lecture covering some, but not all, of the sort of symmetry aspects of the Standard Model. Then we will go ahead to some things that are a little bit more pragmatic, and hopefully getting towards a language that you would be familiar with, drawing Feynman diagrams and things like this, as we discuss the Higgs. Now, as we know, the Higgs was sort of the last piece of the Standard Model in terms of particles, resonances and scattering amplitudes. It was sort of discovered last, but yet I sort of I'm starting with it because I believe that one can understand what's going on in the Standard Model much more clearly if always one has the Higgs mechanism sat in the back of your mind. Then leptons. Leptons are sort of the simplest building blocks in some sense of the Standard Model. Then quarks. so the QCD sector. And then I'm hoping to be able to go below lambda QCD to low energies, to energies where one doesn't talk about quarks and gluons, but instead about things like pions and baryons and so on, because that is a whole other effective field theory that one can derive from the standard model. We have the standard model at high energies, and as we go to lower energies, we can actually derive the structure of this completely different theory. It's also a very beautiful thing. It's called the chiral effective theory, which describes the interactions of pions and things like that. It's also a very beautiful thing because it has its own symmetry structure, which has clues, sort of like a little breadcrumb trail, clues about what's going on at higher energies. By higher energies, I will sometimes say the UV or shorter distances. And so this is an IR theory. It's a lower energy theory. It's an effective field theory, much like we believe the standard model is. And it has all of these wonderful breadcrumbs. So once you understand the UV stuff that we will have already discussed, you will be able to see how these things, the clues for the UV, were pieced together by thinking about the IR theory, the low energy theory. Then I hope to go on to discuss some of the big puzzles in the standard model. So one of them, which follows naturally from considering QCD at low energies, below lambda QCD, is the strong CP problem. This is one of the greatest puzzles we face, and it's really a structural puzzle in the standard model that has existed for many decades now, and both experimentally and theoretically, we are endeavoring to unravel what on earth is going on with this sort of strange corner of the standard model. Another strange corner of the standard model, which is less puzzling in some sense because it's very easy to explain and accommodate, is neutrino masses, and also furthermore their connection to bariogenesis, which is where we came from. You know, it's quite a remarkable fact that we exist, and there's matter. There's a lot more matter than there is antimatter. But within the standard model alone, we cannot really accommodate that fact. So there's a great big puzzle, which is we call bariogenesis, which is just the genesis of baryons, which is really the genesis of, for practical purposes, mostly protons and a little bit of helium. But this is a great big puzzle because we don't know, we cannot yet explain where all that stuff came from. So if a child were to ask you, you know, where did we come from? Currently the answer is, don't know. And it's not even a theological question, although that is an interesting discussion in its own right. It's not even a theological question. It's really a practical question. And at the moment, if we sit down with our equations and calculate, we can't really answer that question. So I'm hoping to touch on that. And then finally, if we have time, I would like to go on to thinking about what the microscopic origins of the weak scale are. As I've alluded to, we believe the standard model is an effective theory because it cannot be, we not believe, we know it is to some extent because it cannot be the full description of nature up to arbitrarily high energies, by which I mean to arbitrarily small distance scales. It breaks down, for a number of reasons it breaks down. So it has to be an effective field theory. There's no other option really. And if we think about it like an effective field theory in the same way that we can think about the theory of pions and baryons, as we go to higher energies, the theory of pions and baryons is described in terms of something completely different, which is the theory of QCD. And we see that the emergence of the pions and baryons is really related to coupling becoming strong in QCD. And similarly, when we think about the effective field theory of the standard model, we might ask, you know, what is above at higher energies or at shorter distance scales? And then one would hope to be able to derive properties like, for example, the Higgs sector parameters, the Higgs mass, from the UV theory, just in the same way that we can, you know, really derive, we can calculate the pion mass by putting QCD on a computer and going to lower energies. So QCD is the UV completion, we say, of the chiral Lagrangian involving pions and baryons. What is the UV completion of the standard model? And this is another enormous question that we cannot quite answer yet, although there have been many attempts and there are many interesting things to discuss on that topic. Okay, so that's the plan for these lectures. I'm hoping I get through everything, but I'm also trying to be realistic about timing. Needless to say, when you're watching these lectures, you know, afterwards, if you have questions, feel free to email me. I'm always available by email, and I'd be happy to discuss anything. Or if you see any errors, and this is the first time I've given this lecture course, so there may be errors. It's almost guaranteed that there will be errors like factors of 2. So please let me know about that if you find any. But also even structurally, if there are some aspects that you think I've explained in a manner that isn't quite lucid, then please let me know, because I can always improve the lectures. Okay, so number 1, what is the standard model? The basic answer is that the standard model is a quantum field theory. And that basically frames essentially all of the properties of the standard model that we know and love, and some of the big mysteries of the standard model. For example, like even one thing that was known as the Eta Problem, which is to do with a particle in below the QCD scale, which is much heavier than we would normally expect, are completely and intimately related to the fact that it is a quantum field theory and not a classical one. So the standard model is a quantum field theory. It is also a quantum field theory that has turned out to be enormously accurate. So the standard model as a quantum field theory means once we've set it up, which we will do in this lecture, we can write down equations that answer certain physical questions and calculate the answers. And it turns out that the standard model does just astonishingly, absurdly, almost inappropriately well at answering these questions. It agrees with an absolute plethora of experimental measurements extremely well, and it has not yet failed in some aspects to answer accurately all the questions we have about the particle world involving the matter that we know. So there are some questions it doesn't answer. It doesn't tell you, for example, at the moment where neutrino masses came from. It doesn't tell you what the dark matter is. So it doesn't answer every question. That's why we have to keep working. But nonetheless, the questions that it is designed to answer, it can answer extremely well. One example, if you consider the electron anomalous moment, anomalous magnetic moment, this is something that we can calculate. I hope you can read that. This is something that we can calculate within the standard model. And it is a truly quantum, there are truly quantum effects, and there is not the classical result. And the electron anomalous magnetic moment, when we calculate it, if we go, all we need is enough smart people to calculate this. So you get some super smart people who can use techniques like perturbation theory to calculate to a very high degree of accuracy what the standard model predicts for this. And what you get is a number that is something like, let me just get this off my iPad, 0.001159652181643 with an error of 764. Sorry, not an error. So that these places are outside the error bar, and this agrees. The measurement agrees to 10 significant digits. Now, this is really astonishing, and it's perhaps one of the most shocking agreements, to 10 significant digits. But nonetheless, it really illustrates that this is a theory that works. All right, so it is not like, let me think of some other theories that you may have encountered. You may have encountered, for example, like the liquid drop model for nuclear physics. And that's a theory, that's a model, you can calculate certain things. but it breaks down pretty quick. We'll start to get things wrong to a few significant digits pretty rapidly. The standard model, no, it's working well. And what that means is that we to a certain extent, we understand certain aspects, especially when it's perturbative, when the couplings are small, extremely well. And we can trust that nature, at least at the energy scales that we can access, nature behaves as a quantum field theory. On the other hand, that also means that when there are puzzles about the standard model that are related to the fact that it's a quantum field theory and we don't understand them, we have to take them seriously. We don't get to pick the answers that we like and ignore the answers that we don't like. And so we know that we're on very firm footing with the standard model in terms of understanding the structure of nature within the energies that we can access. But also, for the same reason, when we're not on a firm footing, we really see that very clearly. And so, for example, dark matter is a very good example. Dark matter is just not in the standard model. And so when we don't see dark matter, we have to take that seriously. Okay, so that's just a little sample to give you some faith that we know what's going on. Now I want to talk a little bit more about quantum field theory. So the standard model is a quantum field theory, and what do I actually mean by that? It's sort of a scary term, considering you're starting out you're at the start of your PhD. So I'll stand over here. You're at the start of your PhDs, and I remember when I started my PhD, I sort of had this notion in my mind that like quantum field theory was the hardest thing to understand, that it was going to be really a big intellectual challenge for me to get to grips with it. And there are varying degrees by which one can get to grips with it. Many aspects of quantum field theory we still don't understand. So even the smartest people on the planet are still struggling to understand certain aspects of quantum field theory. So we're not totally to grips with it, but we are to grips with it enough, to be able to make monumental calculations like this. And so some people are, not myself. And so it is both quite intimidating to start thinking about quantum field theories, but also quite exciting because it's going beyond the sort of thing that you typically learn in your undergraduate degrees. Some undergraduate degrees have aspects they cover it, but not in any enormous depth for the most part. So what do I mean by quantum field theory? So the first bit, quantum, for me, in a very basic sense, this really means that there is a path integral. I view quantum field theories very much from the perspective of path integrals. One can, of course, work with things like creation and annihilation operators. It's entirely equivalent. But I like the path integral approach because it reveals, I think, a little bit more clearly certain structural aspects of what's making a theory really quantum. So when I say quantum field theory, quantum means that there's going to be a path integral, and that path integral will matter. Okay, so and there are certain aspects of the standard model that we can calculate from a purely classical basis, aspects that will never involve an h bar, Planck's constant, in the answer. And those bits don't really care about the path integral bit. They're really more field theory. So when I say quantum field theory, we really will be thinking about things like the path integral. Field theory means it involves fields, unsurprisingly. So functions that are in some representation of the Lorentz group, so they could be scalars or fermions or vectors or whatever, that are a function of the local space-time coordinates. So I'll use phi a lot. So phi would be a scalar field, which is a function of space and time. And so it can take different values depending on where you measure it. That's basically it. And the last thing, theory, which is in some sense, in my mind, the most important part and something we often overlook, which is that it makes predictions. Don't know if you can read that, okay? Yep, okay. A theory makes predictions, and a theory is a hypothesis. At the end of the day, it's a scientific hypothesis, and the standard model is a scientific hypothesis. We've had times in the past where sometimes a theory is so successful, like for example, Newton's gravity, it survived for centuries. And we can sometimes be tricked into thinking that that is more than a scientific hypothesis, that it's actually a great big fundamental thing that's non-negotiable and will always be true. But time and again, that sort of hubris has been punished. And we learn that a theory is always a working hypothesis. It's our best bet. And a really good theory matches experiments very, very well and is very, very predictive. But nonetheless, it is likely to break down at some point. And we know that, for instance, the Standard Model itself will break down at some energy level, energy scale. And so a theory is a thing that makes predictions within its own realm of validity. And it will usually have, as the Standard Model does, some unfixed parameters that you just have to, that you cannot predict. Ideally, we would have a theory with no free parameters that just predicts everything. It's in such a straitjacket theoretically that it predicts everything. We can't change any of the predictions by changing the parameters or something like this. But in the real world, theories will have some free parameters, but then once those free parameters are set, the thing will make predictions. Okay. And how would one define a quantum field theory? Defining a QFT. There's sort of some building blocks. So when we say a quantum field theory, this is what we mean, or what I mean. It involves a path integral, fields, and it's a theory, so it makes predictions. But then how do you really define one mathematically, right? Because in the end of the day, it's not like a sort of philosophical thing. It's not something you sit down with someone, you have a coffee and you discuss, your opinion about blah, blah, blah. A theory is not an opinion. It's really a mathematical structure that makes predictions. And so how do we define that mathematical structure? The first part is that there are some symmetries that define it, or sometimes we might refer to them as redundancies. We won't need to go into that too much for these lectures. So some of the symmetries form the building blocks, the sort of mathematical building blocks of a theory, and we will discuss at length the symmetries of the Standard Model. The second part would be the representations of those symmetries. So these would be the fields. By representations, these are objects, mathematical objects, that transform in some well-defined way under the symmetries. So we say that they are in a representation. And we're used to this. We're used to this even from high school. When we say the electron has charge 1, or -1. That is actually, although we may not have known it at the time, that is actually specifying the representation under U1 QED of the electron. And so that's what a representation is like. We will come back to this. So the symmetries are sort of the building blocks, the foundations. The representations are like what you build on top of those foundations. And then the final bit is some parameters. And these are, handwriting's terrible. These are parameters that can only be determined in most cases by experiment. So they're sort of, in some sense, they're like fudge factors, right? But a theory is not going to be 100% predictive. The Standard Model is not 100% predictive. You cannot predict the mass of the Higgs within the Standard Model. It's not a calculable parameter. It's a parameter that once you do a measurement, and the LHC is under my feet, once you do a measurement, you produce the Higgs boson, and then you can measure where that pole is, where the spike is in the distribution of photons, for example, in the final state. Then you can fix what the value of that parameter is, and that's related to the concept of renormalization to a certain extent. But you cannot, within the Standard Model, calculate it. Although if the Standard Model is the low energy predictive of some more fundamental theory, we would hope to be able to calculate where those parameters come from. So for instance, in the chiral Lagrangian for QCD, involving the pions and the baryons, the things like the pion masses, we can't calculate within the chiral Lagrangian. We can only measure them and then measure them in an experiment and set the parameter to the required value. But in the fundamental theory, in QCD, sorry, I'm going to point out pi, in QCD, the fundamental theory, you can calculate the pion masses from the more fundamental parameters, which are the quark masses and the QCD gauge coupling of the strong coupling scale. And so parameters in a certain quantum field theory that are incalculable are often calculable in the more fundamental theory. And this isn't something that's confined just to particle physics, by the way. You know, the same sort of thing happens in condensed matter as well. You know, for example, the theory of superconductivity, the Landau-Ginzburg theory, has a scalar field, and within that theory, it's just it has essentially what corresponds to, in particle physics, parlay a mass essentially, but that's just a parameter in the theory, and you fix it by experiment. But then when you go to the more fundamental theory, which is the BCS theory of superconductivity, you can actually calculate those parameters in the Landau-Ginzburg theory from the more fundamental thing. So this story of parameters in a certain quantum field theory being incalculable within that theory, but maybe calculable in a more fundamental one, is something that we've seen in many places. Okay. So now let's go on to discuss symmetry. So I will wipe this slide off, and we will now go on to sort of the more technical aspects of this lecture. Although this so far was quite sort of blah, 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 trying to set the scene and get you in the same place that I'm in terms of sort of how we frame these things in a sort of more informal sense. But now, getting a little bit more technical, we'll discuss symmetries. And what do we mean by symmetries, and how do we use them in quantum field theories? Okay, so the first type of symmetries we come across are global ones. And a global symmetry means that there is an operation which essentially leaves the predictions of the theory unchanged. That's a very, sorry, I should sound weird. That's a very sloppy way of describing it, but if you were describing it to someone who does not know any mathematics, that's what we would say, right? We wouldn't talk about things like conserved currents and things like this. And so, for example, take a theory that involves just a massless scalar field, and by theory, I'll start to get a little bit more, sorry, not massless, a complex scalar field. I'll start to get a little bit more technical. And often when I'm talking about a theory, I will write down a Lagrangian. So the Lagrangian is the thing that you integrate over all of space-time to get the classical action. And to make that a quantum field theory, for the most part, you just shove that into the exponent in the path integral, and it becomes quantum when you multiply by I over h bar. So an example would be of a theory with a global symmetry would be the theory of just a boring complex scalar field. So I'll do d mu phi star. D mu phi. So this is what we normally refer to as the kinetic term, for those of you who are not familiar with it. And it's the term that essentially relates to the fact that for this field, for a wave to propagate of this field, it costs you some sort of energy. So if we were to go to the Hamiltonian Formalism, which we can do from the Lagrangian, we would see that these terms correspond to essentially the energy of if the field is not the same at two different places. Okay, and then a mass term, so minus m squared phi conjugate phi. Okay, so now if we make so what's the symmetry here? Well, I'm sure the majority of you will know. There's a U1 symmetry, and by U1, that's essentially the same thing as the symmetry of a circle. Of going around a circle, if you were to draw a circle on a sheet and then of paper and then rotate that circle, it looks the same no matter what angle you rotate it through, and that's a symmetry. And here that corresponds to multiplying by transforming essentially the field by a phase shift. So phi would go to something like e to the I theta phi. And you can see that this Lagrangian remains unchanged. Now, it's not, in a quantum field theory, the symmetry is only really a symmetry of the entire path integral, and all of the physical predictions remain unchanged. So there are certain things that can change. The Lagrangian, in many cases, can change up to things like a total derivative, which doesn't change the equations of motion, for instance. But here, we will just say that the Lagrangian itself is just completely unchanged, because you see you get e to the I theta here. This is conjugated, so we get e to the minus I theta. You get e, so they cancel, and the same thing happens here. So this is a theory with a continuous symmetry, and in this case it's a U1 symmetry, and there's actually will be a conserved current associated with that symmetry. But symmetries can also be, so this is continuous. But we could also have a theory, for instance, with just a boring real scalar field, so not complex. Let me call it, I'll change the name, but I'll call it chi. D mu chi, minus m squared chi. And here we see that there's still a symmetry. It's not continuous anymore because it's a real scalar field, so we can multiply by this by some complex number. We'll just have a complex number at the front here and here, so it won't have remained unchanged. But there is still a symmetry in this case, which is a discrete symmetry, which is chi goes to minus chi, because minus 1 squared is 1, minus 1 squared is 1. Okay, so there are continuous global symmetries and discrete global symmetries. More formally, viewing this in a more technical manner, really, and I think this is in the homework problem, so I won't do it on the board. A continuous symmetry is associated with a conserved current. So this is Noether's theorem. Which was sort of, in my mind, you know, one of the building blocks of theories. You know, symmetries are one of the things you specify, one of the building blocks of a theory. Then the theory of symmetries is like a building block of the theory of theories in a sense. So it's really absolutely foundational. Noether's theorem basically says that for a continuous symmetry, you get a conserved current. And what this means is that really, what I mean by conserved current, which is a divergenceless current. So there's some current, J mu, which will be built up out of the fields in the theory, for instance, for which this always holds. The divergence of that current is 0. And here you can actually build up that current itself. You would get something like phi star d mu phi minus phi d mu phi star, and so on. And I think this is one of the homework problems. So that's what you get in a classical theory, but in a quantum field theory, this is really promoted to an invariance essentially of not just the Lagrangian itself, but indeed the entire path integral. So in the quantum theory, your current would be conserved even at the quantum level. And that actually has some very, very important consequences, because there are theories, we'll come back to this, for which one has a classical symmetry, so not involving H bar. And once you put in the path integral, that symmetry actually becomes broken. So the current is no longer conserved at the quantum level. And that's really one of the biggest and most interesting puzzles that one confronts in quantum field theories. Okay, so that was those were global symmetries. I'll keep that board up. And now I go on to discuss local symmetries, or which are otherwise known as gauge symmetries. Okay, so what do we mean by gauge symmetry? When we gauge symmetry, we really mean that it's becoming a local transformation. And what I mean by that is, you know, in this symmetry transformation here, we were multiplying by the same theta. Theta was just a number, so we're doing a rotation, the same rotation at every point in space-time, all at the same time by the same amount. When you promote it to a local transformation, this means that you can rotate by a different amount in different places. So the rotation over here might be smaller than the rotation over here. I should say that this is not really anymore a symmetry in the same sense as in this case. What this really leads to is more like a redundancy in description. So it's not like different sectors of the theory are really labeled by the value of theta. It's more like once you have a local symmetry like this, or a gauge symmetry, there are just many ways of parameterizing the theory, which will give exactly the same answer all the time. So you will see this sometimes. It's not very useful for these lectures. No, these are not lectures aimed at theorists, so there's no point in really going into this in any great detail. But you should just be aware that occasionally you will hear people say, well, gauge symmetry is not really a symmetry, it's more of a redundancy, and that is true. And it's sort of a historical accident that we call them symmetries. You know, for instance, there's some local symmetries that really don't have a conserved current and things like this. But I'm going to stick with the jargon, because otherwise you would get very, very confused if you were to look at these watch these lectures, and then open a standard textbook which refers to these things as gauge symmetries or local symmetries. So I'm going to stick with the jargon. So what would a local transformation look like? So if we look at this theory here, what would happen if, so we'll stick with the same example, what would happen if instead of doing the same complex rotation at every space-time point, we actually do one that depends on where you are. So now phi would go to e to the I theta multiplying phi, where phi is a field, so it's a function of space-time coordinates. But now theta actually depends on the space-time coordinates itself. So what would happen? Well, if we perform for a small, so let's go for an infinitesimal rotation, so a tiny rotation. So a rotation so small that anything of order theta squared is essentially 0. So then we can do a standard Taylor expansion of this term here and just keep the pieces at linear order in theta and see what happens. Does the theory remain the same? So you can plug this in here, just plug it straight into here. And what we see is that the Lagrangian now, L, goes to L plus some piece that looks like this. Sorry, my phi's are very messy. My handwriting is very messy. Minus phi d mu phi star d mu theta. So theta is now a function of x. So the Lagrangian has not remained unchanged. And this is a big deal. And we can see that the change in the Lagrangian is proportional to this guy here, which is essentially related to the conserved, what would have been the conserved current. And d mu theta now is non-vanishing. When theta was just a constant, it didn't depend on space-time coordinates, then by design, d mu theta vanished. But now it's not vanishing, so we've got this piece. And what do we do with it? So one could, for instance, just say, well, this transformation here is just not a symmetry of that theory, which is correct. But could we modify the theory in some way such that this symmetry really does become, this transformation really does become a symmetry of the theory? And indeed, we can do this. So the way to do it is to essentially promote derivatives to covariant derivatives. By covariant, it means that it will just vary in the same way. Okay, so what does this look like? For this theory, we could write it like this. So I will rub out, so just recall this and then I'm going to rub this out. So we want to promote the derivatives to being covariant derivatives. And what that means is essentially that we introduce a field that we will call the gauge field, which can absorb this transformation. In this case, we will call it A because this is sort of appealing to essentially electromagnetism, an analogy with electromagnetism here. So d mu is no longer d mu, it becomes big D mu, which in this case would be equal to little d mu plus I a mu, where this is a vector field and it's, we call it the gauge field. And it's a field, so it's dependent on the space-time coordinates, a mu of x, sorry. For which the gauge transformation is that phi goes to e to the I theta of x, phi. But covariantly, this gauge field has to also transform. So a mu goes to, I will drop, by the way, for the most part, the brackets with the space-time coordinates in them. You know, I drop it from here and so on because there's really no point writing it out over and over again. So this is just a little reminder, and this is just a little reminder, but this is also a function of the space-time coordinates. A mu goes to a mu minus d mu of theta. So now our symmetry transformation is that we define a local U1 transformation on this field here. So U1, by the way, I said it's the same as a circle symmetry. It's actually sort of, it's the same as SO2, which is the rotation symmetry in the two-dimensional plane. We call it U1 because it's essentially the set of unitary one-dimensional transformations. So this is just multiplying by a complex phase. You see here, this is modulus 1. That's why I keep saying U1. But you can just as well think of this as theta being the rotation angle in a plane or the rotation angle of a circle. Okay. So we define this local transformation to act in this way, but at the same time, the gauge field must also transform like this. And now we see that the gauge invariance is respected because if I've done this transformation, I pick up this piece here. But from these derivatives at the same time, I pick up a piece that's going like the change in a mu, and the change in a mu gives you this guy here. And it cancels, and you see you even have the I that will cancel that guy. So under this definition, L now just transforms to L. So it's left invariant. Okay. And we call this a gauge symmetry or a local symmetry, or depending on who you're talking to, redundancy. Okay, so we have now made the Lagrangian invariant under these local transformations, which is a great start. But, and there is going to be a conserved current associated with this, which is the electromagnetic current, essentially. If you were to promote this scalar field to being instead a fermion, Dirac fermion, then you would essentially have the theory of QED. But there's one piece left out now, which is that there's this new field, but we don't have any kinetic terms for this field. It doesn't at the moment propagate it. There's no notion by which you can have a wave of this field which is moving through space-time. But inevitably it will. So even if you didn't allow for these terms in the first place, they would be generated at the quantum level. And inevitably, there are additional terms that are associated with the propagation of this vector field here. And these terms are known as the kinetic terms, and they're built out of a field which is known as the field strength. So we call this, I wish I hadn't rubbed that off, actually, that was just a mistake. F mu is d mu a mu minus d mu a mu. And you can see that if a mu transforms, so let's call it, just for the sake of using a different index, a alpha goes to a alpha minus d alpha theta of x. These are also functions of x, but this is just a reminder that this is a local transformation. You can see that you will get in here a term that goes like d mu theta, and then here a term that goes like d mu theta, but differentiation commutes. So d mu acting on something is the same as d mu acting on something. So because of the commutation properties and the fact that there's a minus sign here, this thing is anti-symmetric under swapping the indices, that variation will vanish. So this guy here is actually invariant under this transformation, which is great. So now we can build up terms in the theory out of this building block, which is gauge invariant. So once if we're using something that doesn't change under the transformation, then we know that if we build a Lagrangian out of those objects, then you will also get something that doesn't change. And indeed, you can write it now a fully invariant action, which would be L equals minus, we use minus 1/4 as a sort of convention for the normalization. Sometimes you also see other objects in here like the gauge coupling, but we're not going to use it today. F mu nu, and then the old Lagrangian plus d mu phi star d mu phi minus m squared phi star phi. I'll just recall that phi goes to e to the I theta of x phi. So under these transformations, this entire theory is invariant. We refer to this and this as the kinetic terms. As I mentioned before, they're the ones that are associated with sort of the energy of a propagating wave. Okay, finally, we would say that this symmetry is abelian. So what do I mean by abelian? If you don't know the story of Abel, you should. He was a mathematician with a very interesting and a very interesting life. So I encourage you to Google him. But he sort of formed some of the mathematical foundations of essentially the notions of symmetries in maths. And so we say that this is an abelian symmetry because it's a symmetry for which symmetry transformations commute. So if you think about, again, this symmetry as being like rotating a circle on a piece of paper, if you're rotated by an angle alpha and then by an angle beta, you get the same final result as if you'd rotated by an angle beta and then an angle alpha. And what we mean by then is that those symmetries commute, those transformations commute. And so this is a special example of an abelian symmetry because these rotations by this angle theta commute. Two rotations or any number of rotations that you perform, it doesn't actually matter which order you rotate them in, you perform them in, you will always get the same final result. But nature likes abelian symmetries. If you think about it, quantum electrodynamics and electromagnetism, although clearly, humanity was not aware of it at the time, the first gauge symmetry that nature gave us was an abelian symmetry, and that was very generous because had it been a non-abelian symmetry, it may have taken a lot longer to understand nature. So we were sort of lucky. Or perhaps, the easiest bit to understand of the standard model is the abelian symmetry, and that's why we figured it out first. But there are also non-abelian symmetries. So I'll probably I'll change color for this. There are non-abelian symmetries. And in that case, in the case of a non-abelian symmetry, it really does matter what order you do things in. Okay. So for non-abelian symmetry, we say that the action of the symmetry on any given representation does not commute. And I know this is an experimental audience, so I'm trying to not use too much mathematics, but that's basically what it corresponds to. And you will be familiar with it, I'm sure. You've worked with matrices during your undergraduate degrees, so you'll be aware of matrices that don't typically commute. And so there are still symmetries where you can perform an operation on a representation, and it really does matter which order you perform operations in. And one example, the example that comes up in the standard model is an SUN symmetry. So SUN is, SU means special unitary group of degree n. And so it's sort of like, we think of it as being like having n pieces. So SU2, so U1 is the unitary group of size 1 essentially, so that's just multiplying by complex phases. So then, you know, the matrix e to the I theta, which is a 1 by 1 matrix, multiplied by its conjugate gives you 1, so that tells you that it's unitary. If you were doing, for instance, SU2, you'd have a 2 by 2 complex matrix, and U, let's call it M, then M dagger M would be the identity matrix. That's a unitary transformation. And it acts on the representations, and the representation we will come across in the standard model is just the fundamental representation, which is just an n-dimensional complex vector. So I keep doing things out of shot. It's an n-dimensional complex vector. So now our space-time field is no longer, I'm going to put a little line under here, the field, an underscore, just to remind you that now this is like a complex vector made up of space-time fields. So you'd have phi1 of x. It's just a little reminder. Always fields are functions of the space-time coordinates, but sometimes I'll just write that explicitly as a reminder. All the way down to phi m of x. Okay. And the symmetry acts on this big phi in the following way. Phi goes to U, where U is an n by n matrix, times phi, where U is unitary. So U dagger dot U is the identity matrix, the n-dimensional identity matrix. So that's how it acts on it. And this is already familiar now from this abelian version here. We're just multiplying by some number. And now you just have a vector and you multiply by some matrix. And if the theory is invariant under this symmetry, you have a non-abelian symmetry. Sorry, invariant under this transformation, you have a non-abelian symmetry. And we call this guy here a representation under the symmetry. And in this case, it's the fundamental representation. Okay. So we will come across, the only types of representations we will come across in the standard model are fundamental representations. They're fermions in most cases. So, oh no, that's not quite true. These are, this would be a field of a vector of fermions for the sort of matter representations we come across. We won't talk about a huge amount, but the gauge fields themselves will be in a representation called the adjoint representation, which just transforms in a slightly different way. It's sort of like matrix multiplication, but on both sides. But in principle, you could have much more complex, much more involved representations. You could have, for instance, representations that are tensors that have many, many indices, and that represent the symmetry transforms those indices in perhaps even different ways and things like this. So there are many different types of representations one can have. Apparently, nature just chose relatively straightforward representations, and we don't know why. Okay, so more generally, an object with a sort of a well-defined transformation property like this, that allows to have a group action acting in a similar manner to matrix multiplication, is something that we call a linear representation or linear action. The transformation is linear because it's just multiplying. So all of the pieces transform in the same way, in a well-defined way. We refer to this as linear. Sometimes, and we will get to this when we go to spontaneous symmetry breaking and things like this. In the future, we will discuss nonlinear representations, which is a different way that objects can transform, which is not as simple as a matrix multiplication. So this is just a little primer in case we come across this. Well, we will come across this later. Okay. I think it's probably best. Oh, no, let's try and do just 5 more minutes. Okay, so how do we form an invariant Lagrangian now from this guy? So we've got this vector. Well, it's actually quite simple. So for a global symmetry, for a global symmetry, we will do something that's actually quite similar to what we did for the abelian case. So now the Lagrangian will look like this. So we'll have the kinetic terms, we've got d mu phi, but now we call it phi is actually a vector of phi's. So we don't just do the complex conjugate, but we do the Hermitian conjugate. So we transpose it and conjugate it times d mu phi minus m squared phi Hermitian conjugate dot phi. And you see, for instance, this is very clear here. We would get u acting on this side and u dagger on this side, but u dagger u is just one, the identity matrix. So you just get the identity matrix here. And the same thing, if it's global, then it doesn't even know that then the symmetry transformation does not depend on any space-time coordinates. So the derivatives don't matter. And you just get u dagger u, which is just one. Okay. For a local symmetry, things change a bit. So I'll rub off this. This is very straightforward. For a local symmetry, things are slightly different, as they were for the U1 symmetry that we've already studied. For a local symmetry, now the transformation is space-time dependent. So for the U1, the phase theta itself was space-time dependent. And here we have to do that, but in a non-abelian way. And it just turns out that the matrix U, we can actually completely parameterize it in terms of objects known as the generators. And now a bunch of fields. Last time it was just one field, theta. But now we have a bunch of fields, one for each generator. And the number of generators is actually the same as the number of the gauge fields. So for SU2, it'll be 3. For SU3, it'll be 8. For SU theories, it goes like n squared minus 1. And we can parameterize any unitary matrix. That this is what specifies the number of generators and their form, how they interact with each other, essentially. That any unitary n by n matrix can be parameterized in this way with n squared minus 1 generators. And here now this unitary matrix depends on the space-time coordinates. And all we do now to make our theory invariant is exactly what we did for the abelian case. We promote our derivatives to covariant derivatives. So now L, it becomes big d mu of phi, Hermitian conjugate, then big d mu of phi minus m squared phi dagger of phi. And now the covariant derivative, big d mu, is, in this case, it is, because I've not put any gauge coupling yet, we're gonna put that back in the future. D mu plus I a mu ta, where each a mu transforms just like in a manner similar. It's not quite the same. In a manner similar to the ways that the way that a mu transformed for the abelian case. So when we promoted the derivatives to the covariant derivatives, this Lagrangian remains invariant under this transformation, and we can also add a kinetic term for the gauge field like we did for the U1 case. And that's why we say it's covariant, because what it really means when we say it's covariant is that with the covariant derivative, d mu phi transforms in the same way as phi itself. So it doesn't really change the transformation properties. So then if we build the theory out of blocks like this, we at least know that that is transforming in the same way that a fundamental transforms. So if we contract it with other fundamentals, other things that transform as fundamentals, we can easily build a theory that is invariant.